How do you get better? Well, make sure you come to every session, and we'll try to keep it lighthearted. There aren't as many jokes in Calc 2 as there are in Calc 1. Calc 1 is really fun. Calc 2, we'll have a few, but not so many. Do as many problems as you can. The harder the problems are, the better they are, because it's going to force you to think. And more than likely, it's going to force you to get stuck, and you're going to get frustrated. And that's a very common thing, to get frustrated. Now the question is, what do you do with that? Well, some people use the frustration as a decision to say, well, I shouldn't be doing this. I should stop and give up. That's the wrong thing to do if you're frustrated. You should use the frustration to motivate you, to push you, and to think harder. And when you're frustrated and you finally see that solution, you're going to be like, I can't believe I did that. I'll never make that mistake again. Well, if you're not frustrated and you see the solution, you're like, yeah, of course, it's obvious. Well, is it? No, maybe not. Not so clear. Make sure to ask for help. I think a lot of people, for whatever reason, they don't like to ask for help. They might see it as a sign of weakness. And I don't think that. And I know that it's hard. You have to overcome that barrier. But if you don't know what's going on, if you don't ask for help, you're still going to not know what's going on. And it's just going to get worse and worse. The sooner you figure out what's the right thing, the better it is for you. The last thing here is don't be afraid to make mistakes. You might make a lot of mistakes. That's okay. I mean, a lot of you are going to be engineers. And you should realize you're going to make lots of mistakes. If you don't want to make mistakes, switch to art history. Life will be good. You can live a carefree life. But you're engineers. You're going to make mistakes. That's all right. Because mistakes are opportunities to learn. Nobody will get through without making mistakes. But what you can do is you can learn from your mistake. In fact, mistakes are wonderful chances for you to say, aha, here's something I don't know how to do yet. But let me figure out why I made that mistake. And then I'll try something else, because I won't need to make that same mistake again. So mistakes are very useful. And there's another comment I have here, which is, don't just focus on memorizing procedures. If I see this, I do step 1, then I do step 2, I do step 3, and I circle my answer. Understand why we do things. If you can understand why we do things, first off, it's a lot more fun. But second off, you're a lot more powerful, because then you're ready to adapt to new situations. One of the things we often do is we say, okay, we know what we've taught you. So we know what you know. What we'll do is we'll take an idea and turn it around. So instead of giving you the input, we'll give you the output. And then you have to figure out about something going backwards. If you understand why things work, it's very straightforward. But if you don't, you're going to struggle. All right. So now we're ready to start calculus. And I like to have a very short course on calculus. I learned this when I was about your age. So it starts by saying the following. We understand flat things pretty well. Now, when we say a flat thing, we mean things like lines, rectangles, boxes. In 3 dimensions, we have planes. These are the types of things that we understand, things that we're comfortable with. The problem is, what's around us isn't flat. Instead of a straight line, we get something with lots of wiggles. Instead of a rectangle, we get some sort of a blobbish shape. Instead of a box, some sort of bent tube, and so forth and so on. So the thing is that what we're good at doing is what is not really relevant. So how do we put these things together? The answer is, we approximate things which are not flat by using things which are flat. That's what calculus boils down to, is we're going to learn to do good approximation by using flat things. That's all of calculus. All right, so let's start with the first half of calculus, which is differential calculus. Now that asks the following question. How are things changing? What's the rate of change? Now, for some things, it's really easy to answer that question. So the easy case is what? A flat thing, which is a line. For a line, the rate of change, when I talk about rate of change, it's how does one thing change with another? And we call that our slope, which looks at our change in y over change in x. So oftentimes we use a delta for our change. So again, a flat thing, very easy to understand. But now the question is, what if what we have is not flat? Maybe it's very bumpy. We ask the same question. What's the rate of change? And the proper answer is, well, it depends. Because it's varying. It changes from place to place. So, okay, so now we say, all right, what's the rate of change right there? All right. Now we say, that's a good question. Well, what can we do? Well, the answer is we pull out our magnifying glass. All right? So we pull out our magnifying glass and we zoom in a little bit. And when we zoom in, we'll see something that looks like that. And there's our point. We say, okay, good news, it's a lot less bumpy. But we could do better. We say, yeah, we could do better. What we'll do is we'll pull out our microscope. And we're going to zoom in even closer. All right? So we zoom in even closer. And what do we see? Well, we see something that's looking even less bumpy. Say, good. But is that enough? Well, we go to physics. Say, all right, let's use our scanning electron microscope. And we zoom in really, really close. We can't go to the math department. We don't have the budget for that. Okay, but we zoom in, and what do we see? When we zoom in really close, lo and behold, after coming in closer and closer and closer, what we see is that our bumpy thing looks flat. And it looks like a line. Now we can say, hey, this thing is a line. I can talk about that slope. Now this particular line that it starts looking more and more like has a name. It's called the tangent line. And so we look closer and closer and say, okay, it's behaving like a line. I know how to answer the question for lines. Now I can talk about how things are changing. So that's what happened in differential calculus. Now in order to do this, of course, we had to deal with one really important idea. And that idea is the following. Namely, we had to be very, 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 very close. You had to keep zooming in. Zoom in more and more and more. So the question is, well, how do you actually do that? Well, the answer is one of our favorite things. Limits. So the way we think about zooming in, and looking at something as we get closer and closer, is we talk about a limit process. So limits are built to answer the following question. What should happen? Now, the thing is, we can't know what happens at the point we're interested in, but we can talk about what's happening near the point that we're interested in. So that's what limits are for. So let's do a really simple limit. Here's the limit as t approaches 2 of t squared minus 5t plus 6 over t minus 2. And we can say, okay, well, what happens? Well, the first thing you almost always do with limits is you plug in, and we see it's going to 0 over 0. And when we see 0 over 0, what do? More work. More work. Now, a few people are like, oh, I know what to do. L'hôpital. Yeah, you can do it, actually. It's fine, because we know l'hôpital. And it works perfectly fine. Now, if you don't like l'hôpital for some reason, you don't like, to go, oh, it ruins your voice or something. But you don't have to. But we could. We might as well. It's just as fast. So if you did L'Hopital, and yes, you can do L'Hopital. Now you're probably thinking, wait a second, are we going to be doing limits this semester? Not too much, but we will a little bit. So if you do L'Hopital, which means take the derivative of the top, derivative of the bottom, it's like the really nice quotient rule, the way you wish the quotient rule worked. So that's L'Hopital, if you remember. And if you do that, you say, okay, that take the derivative of the top would be 2t minus 5, derivative of the bottom would be 1. Now you plug in 2, what do you get? -1. Now, the other way you could have done this is t squared minus 5t plus 6 actually factors. You will be amazed at how often things factor in this class, almost as if we want them to. And then you see, aha, the t minus 2 terms cancel. So in essence, what's happening is when you cancel off the t minus 2's, you're canceling what causes the zeros. Now, I will tell you we will do limits in this class, but most of the time when we do limits in this class, we're going to be doing sort of the opposite of what's happening here. And by the opposite, I'm going to say, instead of looking at when do things get smaller and smaller and smaller, we're going to say, what happens when things get bigger and bigger and bigger? So most of the limits we're going to look at involve infinity, which is the same process, actually. There's really not much different. So once you have the limits, you can, of course, talk about the derivative. And what's happening is when you talk about the derivative, you really zoom in. And the way you zoom in, find that slope of the tangent line, is you look at these slopes of secant lines. You don't need to know this formal definition. It's just a walk down memory lane. The good days of Calc 1. Now you might say, this seems to be a terrible way to take derivatives. You are correct. It is a terrible way to take derivatives. So what are we going to do? Well, the way we actually take derivatives is we start with our definition, and then we build up a collection of rules. And so there's a set of functions, and there's 8 of them listed here. And these are our basic building blocks. You should know all these derivatives. At some point in the semester, you will need to take a derivative of pretty much everything on that list, for some reason or another. Now, quick recap. Derivative of x to k. For any choice of k, is kx to k minus 1. Derivative of log x is 1 over x. Derivative of e to the x, e to the x. Really hard to change e to the x's mind. They're very stubborn, e to the x. Derivative of sine is cosine. Derivative of cosine is negative sine. That negative is going to throw a lot of people off. Derivative of tangent is secant squared. Derivative of secant is secant tangent. And of course, the best one. The masterpiece, if you will. The derivative of arctangent is 1 over 1 plus x squared. It's a glorious function. Glorious function. Now, of course, there's not just the rules for the building blocks. You also have to have the rules for putting them together. So what rules do we need to know? The rules you need to know, actually not so bad, are the fact that derivatives are linear, which means that they work really well with addition and pulling out constants. You need to know the chain rule. The chain rule is probably the most important rule when it comes to taking derivatives. So chain rule is a function inside of a function. Derivative of f of g of x is f prime of g of x times g prime of x. You need to know the product rule, which is when you have two functions multiplying together, f of x times g of x. Now when you take the product rule, it's not that you take the derivatives of each one and multiply them together. The way I like to think about it, everyone gets its turn. So it's like, all right, we'll say, first off, f, you get to be the derivative. So it's f prime, and g has to wait. Now it's g's turn, so it's g prime, and f is normal. So f prime of x, g of x, plus f of x, g prime of x. The other rule which you might need is the quotient rule. I will say we might from time to time use the quotient rule, but really the first three are the most important. And actually, if you know the first three rules, the quotient rule is not really necessary. The reason I say that is that if we think of f of x over g of x, we can write this as the derivative of f of x times g of x to the negative 1. Then if we use combinations of the product rule and the chain rule, it actually pops out. So the first three rules are the most important rules. And once you understand your basic building blocks, your basic functions, and your rules for combining things together, you can take basically any derivative. They all behave more or less the same. It's very mechanical, very rote. You just have to be patient. And so taking derivatives is pretty good. We tend to do pretty well on those. All right, so we should take the following derivative. So let's, anyone have a favorite function? We'll just do one really quick. Any function you wanted to see the derivative of? You're like, man, I've always wanted to see what the derivative of that function is. No? Well, we'll make one up. E to the x arctangent x squared plus sine 5x cubed. Something simple. All right. What are our rules? Well, we're going to use the fact that derivatives are linear. Why? Because of that plus sign. The plus sign says, whenever you have a plus sign, break it up into two parts. So we're going to take each part separately. So let's talk about this first part. What's our big rule? Our first rule we're going to pull out. Product rule, right? Because I have two functions multiplying together. Now e to the x, that's okay. When we come to, okay, so derivative of e to the x would be what? Well, e to the x. Second one stays as is. Now, e to the x stays as is. Derivative of arctangent of x squared, what rule do you need? Chain rule. See, it may not look very complicated, but see, we're using all these various pieces here. Okay, derivative of arctangent. Now, derivative of arctangent is 1 over 1 plus whatever's inside squared. So, 1 over 1 plus the inside squared. X squared squared. Okay, so is that the right derivative of arctangent of x squared? And why not? Chain rule, right? Because we need to multiply by what? 2x, right. Multiplied by the derivative of the inside, which I'll put that up here. Okay, derivative of sine. Yeah, positive cosine. What goes inside? Yeah, right. Leave the inside alone. It didn't do anything to you. Leave it alone. All right, and then what? Chain rule, so we have to do 15x squared multiplied on the end. And we can circle our answer. Because we don't have to simplify. I mean, sometimes we do. But most of the time, it won't tell us to simplify. Usually, if it's asked us to simplify, it's because the answer is really beautiful. All right, so that's our differential calculus. Now we switch gears. Because there's two kinds of calculus. So the second kind of calculus it's called integral calculus. It's a different question. And the question is, what's the total? Now, you might say, total what? Oh, fantastic question. We'll get to it, and the answer is, it could be lots of different things. Oftentimes, we start by thinking of area, and that's a really good way to think of it intuitively, but we'll see things like volume, mass, work. If you get into economics, it can be things like money. It can be pretty much anything. So whenever you're after a total of something, that's when integral calculus comes into play. Now, when we did differential calculus, we said, hey, here's something which is easy to find the total of, so we should do the same thing here. So what's an easy thing? Well, an easy thing would be a rectangle if we think of things as area. Well, why? Well, because a rectangle, how do you find the area of a rectangle? Base times height. So the area is really simple. But now you might say, well, what if we don't have a rectangle? Maybe we have something which is a little bit bumpy. And we're like, well, I want to find this area here. How can we find the area of this piece? It's not a nice flat thing. It's all bumpy on the top. So we say to ourselves, we've got to somehow figure out how can we approximate this by something which is flat. So what's the idea? Do you remember? We break it up. We cut it into parts. right? Why? Well, when we cut it into parts, if we look at any single part, what does it look like? It looks kind of like a rectangle. It's not perfectly a rectangle, but it's a lot closer. Now, how can we make it even better? Divide up even into smaller parts. So here's the notion of closer and closer means divide up into thinner and thinner slices. So integration is about breaking things into small parts, understanding each part, and putting it back together. So now the key here is we say, all right, look, a rectangle, a small slice is approximately a rectangle, which means I can approximate the area of one of these little pieces by saying, well, let me treat it like it were a rectangle. I add all the little parts together and I get an approximation. Now the nice thing is, as I chop things up smaller and smaller, my error, how far off I can be, gets smaller and smaller, and therefore I get a better answer. All right. So that's the basic idea of integration, what we just said. We take what we're looking for and we divide it into many small parts. We give a good approximation to each part, and then we add them all back together. And when we start talking about applications of integration, which will be in a couple of weeks, you're just going to remember this theme over and over and over again, because we're going to keep doing it over and over and over again. It's the way integration always works. Break things into parts, understand the small parts, put it all back together, and life is good. Now, again, we have to make sure our parts are very, 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 very small. And what we get is, over here, you'll see we're adding up, so it's a summation, and these two things are what? Well, it's the height times the width. So that delta xi is a change in the input. The f of xi is the height. So essentially, you have a height times width. This is a little rectangle. We add them together. And we say, as you get smaller and smaller, we indicate this value by an integral of the function dx. The dx means something. dx has meaning. And so we are going to be very particular that you've got to write down that dx. If you stop writing down the dx's, you're going to lose a lot of points. And maybe it's just 1 point per problem. But you got a lot of integration to do this semester. So they'll add up. So make sure you get the dx. By the way, do you remember what this symbol came from? Or the way to think of it? It's like an S that you've stretched out. Why S? S for sum. Integration is about adding things up. Over here, this doesn't look like an S, but it's a sigma. Notice it starts with an S for sum. So you should always think, S for sum. We're adding things together. Now, just as we had some basic rules for differentiation, there are some basic rules for integration. What are they? Well, if you don't do anything, the output is 0. So A to A says, look, I start and stop. I'm not adding anything up at all. So I'm getting 0 out. Orientation matters. This is going to be a big theme when you hit Calculus 3 next semester. But if I go from A to B, and if I flip it, going B to A, I need to put a negative in. So orientation matters. It matters which way you go. Integration is linear, which is just a way of saying it works really well with addition. And you can break up over addition, and you can pull out the constants. And the last thing is you can combine integrals together if you have intervals that sort of match endpoints. So if I go A to B, B to C, so the key here is notice that these match. So A to B, B to C is the same as going A to C. It has no bearing at all how A, B, and C are related to each other. Now these are some basic properties, but then there's the real question, okay, how do you actually integrate? What's the procedure? Well, The answer is you do something a little fun, the mental. So the fundamental theorem of calculus, when people think about integration, they oftentimes think of the fundamental theorem of calculus, which is to say, the way I integrate something is I find an antiderivative, and then I evaluate. So that's one of the fundamental theorems. It says, if I want to integrate this little f of x, all I have to do is find the antiderivative of little f of x, we'll call it capital F of x, and evaluate it at the endpoints. And that works. It's an amazing result. Now there's a second version of the fundamental theorem of calculus, which says, you know, if you're taking a derivative of the integral from a to x of f of t dt, that's the same as f of x. We will not use this very often. We will primarily focus on this first part. I do want to mention that finding antiderivatives is a wonderful tool, and that is what we will spend a dramatic amount of time in our class doing. But the idea of integration existed long before differentiation. We're talking over 1,000 years. So you can do integration without ever having to appeal to antiderivatives. It's just really, really tough. So be careful. You shouldn't think that, okay, whenever I look at an integral problem, I always have to find an antiderivative. One of the things that we hopefully will try to convince you of is that it's really hard to find antiderivatives. And in many cases, it's essentially impossible. Not that they don't exist, it's just that there's no clean way to write it out. So it's going to take work. As it says here, integration is art. Differentiation is rote mechanics. You know a dozen rules, life is good. And you can take a derivative of anything. It takes almost no effort at all to write down a function that nobody can find an antiderivative of. So which is why you'll see that we'll ask for fewer suggestions from the audience. When we're taking derivatives, it's like, yeah, give me any function, life is good. When we're doing antiderivatives, it's like, well, give me a really particular type of function. Then we can do it. Now, what antiderivatives should you know? I say that there are 10 of them that you should know. And they're the ones that are there right there. And if you look at it, the ones on the right here, these 8 should look really familiar because they are coming from the rules for derivatives. We just run it backwards. So, for instance, when we took the derivative of arctangent, we got 1 over 1 plus x squared. So now if I have 1 over 1 plus something squared, here I've been using u instead of x, I should get arctangent back. So these 8 are essentially the same things that we saw when it came to rules for taking derivatives, just swapping the roles. The last 2, these are not hard to show. And because tangent and secant are important because they're trigonometric functions, they got added to our list. So the integral of tangent is log secant. The integral of secant is log of secant plus tangent. This is not a very long list of antiderivatives, and I will say this now, and I'm going to say this again next time. We are not going to increase this list. So when it comes to things where you actually know an antiderivative of, it's this list. That's it. That starts and stops here. And so this is where we're going to have to work. Now you might say, but wait a second. There's so many more functions out there. What do we do with those? The answer is, well, we use tools. There's lots of tools available to us. And things like using algebra, using trigonometry, in some cases using symmetry, various other things. The most important tool of all, the best one, is the substitution rule. Now the substitution rule comes from the chain rule. So essentially they said, let's start with the chain rule, because that's a rule for differentiation. And let's figure out what it becomes if we think about it as a rule for calculus. So remember the chain rule says if I have the derivative of f of g of x, that's f prime of g of x times g prime of x, you integrate both sides. Well, essentially I'm integrating over here, instead of f prime I put f, and so I want to integrate something where I have a g of x on the inside, g prime of x dx. And what we can do, the idea of substitution is to introduce new names. And using this idea of like, let's just change what we call things, it's a really powerful tool. So we can say, let's introduce something, we'll call it u, and we'll replace g of x by u. Well, how does du look? What does the change in u look like? Well, the answer is, you take the derivative, it would be g prime of x times how x is changing dx. So this becomes du. So it becomes f, now it's a function of u, du. And we can simplify. Almost all the things that we learn about in integration basically boil down to the following. We only know how to take the antiderivative of 10 things. So we have to figure out, how can we simplify what we're currently working with to get us to one of those 10 things? And that's it. That's what we're going to be spending the next 3 weeks on, is how do we get there? And so we're going to learn all sorts of fun things. We can also do this, by the way, with definite integrals. The thing to remember is that if you ever do a substitution, you have to update all the variables. So if I'm doing an integral from a to b, when we write a to b, we really write x equals a to x equals b. See, these are x variables. So if we switch over to here, we need to write in terms of u variables. So the question is, well, how do we figure out what u should be? The answer is, if we know what x is, we plug it into the relationship. The relationship is u equals g of x. So plug in x equals a, we get u equals g of a. Plug in x equals b, we get u equals g of b. Let's try an example. So we're going to do a nice warm-up, right? We've got a lot coming this semester, so we should start by warming up. So find the integral from 0 to 1. It's a definite integral, and a lot of the integrals we're going to do when we hit applications are definite integrals, so we should get used to them. Integral 0 to 1, 2x squared of 1 minus x to the fourth, plus e to the x over 1 plus e to the 2x dx. Now, of course, what we have here is we have our favorite thing, plus. We like plus, because plus is a way of saying we can break things into parts. And so if you can break things into parts, you should do it. 0 to 1, 2x squared 1 minus x to the fourth dx plus integral 0 to 1 e to the x over 1 plus e to the 2x dx. Now, we can do these separately. So how do we do it? Well, they're not on our list of 10, so we start looking for things that we can do, substitutions that we can make. Now, when you're thinking about substitutions, what do you look for? Well, there's 2 places to look for substitution. So where are your 2 places to look? The answer is, namely, let's write this down. Oh, sorry, it takes a second here. So place number 1 is function inside of a function. So we're going to look on the inside. All right. But that's not the only thing we should be doing. The other thing to look for is to say, all right, look for a good derivative. Because when we do this, we have this piece here. Try to say, well, is that the part that's our derivative? Can we make it work? So let's look at this first one, for instance. This 2x, if I think of that as our g prime of x, that says, oh, if we had an x squared, because if I take the derivative of x squared, that gives 2x. Now the question is, does that make sense? Well, it's not x squared on the inside, but x to the fourth is not far off. See, x to the fourth, I can think of this as 0 to 1, 2x square root of 1 minus x squared squared. And now we're like, ah. So this would be a good substitution. U equals x squared. Du is 2x dx. So what do we get? Well, we get integral 2x dx becomes our du, and then we have square root of 1 minus u squared. Now, we got to think about our bounds. Our bounds. See, these bounds are x bounds. It's not just 0 to 1. It's x equals 0 to x equals 1. That's our bounds. Our bounds are 0 to 1. So 0 to 1 were our old bounds. Our new bounds are 0 to 1. Now wait, what? Okay, it's u equals 0 to u equals 1. So what happens is it turns out that 0 squared equals 0, 1 squared equals 1. It's sort of a coincidence. We did actually change our bounds. Well, let's go ahead and finish this part. Do we know the antiderivative of square root of 1 minus u squared? Not yet. We will soon. Stay tuned. But maybe we don't have to know. Because look, it's a definite integral. Square root of 1 minus u squared isn't just anything. It's a circle of radius 1. And in particular, I can say that this integral, I can think of as being the area of 1/4 of a circle of radius 1. So, I know that a full circle of radius 1 would give me pi, so 1/4 of that would be 1/4 pi. All right, so that's the first piece. Now let's go to the second piece. Here we have e to the x over 1 plus e to the 2x dx. Maybe it's not so clear what's the inside function, but is there some piece that's a good derivative? And the answer is, well, yeah, that e to the x, that's beautiful, because e to the x, it's that derivative where the derivative of e to the x is e to the x. So this is suggestive. Let's let u equal e to the x. Then what will du be? Well, e to the x dx. So this is our du. And what do we end up with? Well, we'll have du upstairs, so 1. What about the downstairs? Well, I have to write everything in terms of e to the x. So e to the 2x, it turns out e to the 2x is the same as e to the x squared. So I can think of this as 1 plus e to the x squared, or 1 plus u squared. Now, what are our bounds going to be? Well, we plug in 0. So e to the 0 is 1. And we plug in 1. E to the 1 is e. And 1 over 1 plus u squared, that is on our list of things we can integrate. This is arctangent of u. So we can find the antiderivative evaluated from 1 to e. Notice I'm not going back to the substitution for x. I don't have to. When we're doing a definite integral, we always move forward. We never move back. So what is that? Well, that's arctangent of e minus arctangent of 1. Well, wait a second, arctangent of 1, we know that. That's pi over 4. Because if I take the tangent of pi over 4, I get 1. So the arctangent of 1 is pi over 4. And arctangent of e, we know that that is arctangent of e, because you can't really simplify that. Now remember, we've got to combine these two answers together. So I get a positive pi over 4. This is actually going to be a negative pi over 4, which means that these parts cancel. So the final answer is arctangent of e. Or you could call it arctane, but I don't think you should call it that, because that's not really a word. All right. Good. That was a nice warm-up. Let's try another one. Find the integral of e to the y plus 1 quantity squared dy. Well, that doesn't sound so bad. Now, what happens? Well, a lot of people would be tempted to do the following. So this is our temptation. Now, you can probably guess, because I'm writing down our temptation, it's not good. But let me write down what it might be. A lot of people like to think, well, let's think about chain rule. So it's like, oh, I would just integrate the outside, e to the y plus 1 cubed, and then I put a 1/3 in front, and then I divide by the derivative, or the integral of the inside, right? So it's like, when you do the chain rule, you multiply by the derivative of the inside here, maybe you divide by the integral of the inside. So this is what a lot of people would be tempted to do. Now, this is wrong. It doesn't work. So unfortunately, you cannot just do this kind of operation. It gets you the wrong answer. And I know it feels like it should, but it won't work out. And you can go through and you can actually take this derivative, and if you take this derivative, you will get that part of this derivative is e to the y plus 1 quantity squared. But then you'll get another piece, which shouldn't be there, because you shouldn't have anything else when you take a derivative. So be careful. Don't yield to temptation. So how can you do this? Well, the answer is, let's use our algebra skills. So there's this square here. What we can do is we can expand, or if you like, FOIL. So it says you're taking e to the y plus 1 times e to the y plus 1. And if you multiply that out, you're going to get e to the y times e to the y, which is e to the 2y. Then e to the y plus another e to the y. So that's 2e to the y and plus 1. And now, each part here, this is all reasonable. So you end up with the integral of e to the 2y is 1/2 e to the 2y. Integral of 2e to the y is 2e to the y. Integral of 1 is y. And because we want all the credit, full points, don't want to lose any points, plus c. And now you can convince yourself these are definitely not the same thing. So be careful. Be careful, the right amount of careful. Now, you should sort of start picking up on a theme, and let's do one more problem. We'll just make one more up. So I want to point something out. All right, so let's try the following. Let's find the integral of 3x cubed, divide that by 2, plus the square root of x squared plus 4 dx. Now, our first temptation is like, we get to drop 4, right? Maybe this will be the one we drop. The answer is no, we're not going to do that. No, we're going to figure out what to do. So here, a key idea that we're going to keep seeing over and over again is figure out how can we rewrite, how can we simplify. That's our goal. Is if we can figure out how to rewrite things and simplify things, then perhaps we have a chance to make things work. So in our case, we say, well, let's really try to get rid of the complicated things. The square root downstairs, we'd like to get rid of that square root. So what we can do is we can go to algebra, and then algebra tells us there's a great way to get rid of that square root downstairs. Namely, we use what's called conjugation. So I'm going to multiply top and bottom by 2 minus the square root of x squared plus 4. All right, now what happens? Notice I'm multiplying by 1, and multiplying by 1 is perfectly allowed, no problems. Now, downstairs, when you multiply that out, we're going to get, let's see, let me do the upstairs. First, 3x cubed times 2 minus the square root of x squared plus 4. And as I said, downstairs it's a plus b, a minus b. So it's going to become 4 minus the square root of x squared plus 4 squared would be x squared plus 4. Now we say, aha, the 4's cancel, and we are in our best scenario possible. We have gone, instead of this long expression for the denominator, it's now x squared. You can't get much better than that. And x squared can divide into x cubed. So that's also really promising. So if we do that, and the minus can move up, what do we get? Well, we get the integral of minus 3x times 2 minus the square root of x squared plus 4 dx. Oh my gosh, I forgot the dx up here. Don't forget. Notation is important, and it gets more important the further you go. All right, now what do we do? Well, from here, the next thing to do is distribute. So this will be the minus 3x times 2 is minus 6x. Minus 3x times minus is plus 3x square root x squared plus 4 dx. All right, well, what can you do here? Well, the answer is you can break up over your addition. So I can write this as minus 6 integral x dx plus 3 integral x square root x squared plus 4 dx. All right, well, we'll treat these separately. See, that's a nice thing. So the integral of x, well, that's not bad. That would be 1/2 x squared. How about here? Well, here, it's not so clear what to do. But, say, it's kind of similar to what we were doing a minute ago, right? We got this x squared plus 4 on the inside. Here's this x on the outside. Let's let u equal x squared plus 4. Then we'd have du is 2x dx. I can divide both sides by 2, so that'd be a half du is x dx. So what do we get? That would be 3 halves, because there's a half coming from there, and there's already a 3. Integral of square root of x squared plus 4 becomes square root of u, which in calculus becomes u to the 1/2. And then the x dx becomes the du. We already have the half. So let's see what we have. So that's minus 3x squared here plus 3 halves. Now we're going to integrate u to the 1/2. So that would be u to the power 3 halves. And then you multiply by the reciprocal, which is 2/3. And of course tack on a plus c. Now 3 halves and 2/3 simplifies really nicely, which is good news. We still aren't done because that u can't stay as u. We've got to go back to x. If we start with x, we have to end with x. So to finish this off, we have the minus 3x squared plus u was x squared plus 4 to the 3 halves, and then plus c. And there's our answer. Now, here's the thing I want to point out. This is a really sort of a nice idea, in that you're going to see this as a theme coming forward. When it comes to plus, there are 2 kinds of pluses. There's the good kind, and these are the kind where we look at it and we're happy. Now, what's a good kind of plus? All right, let's point out where we used a good plus. The answer is the good kind of plus is right here. See, what's special about this plus? Because it's a function plus a function. It allows us to pull things apart. That's the good kind, okay? But there's also a bad kind of plus. Now, what do we mean by a bad kind? It's the kind of plus that when we see it, we go like, oh no, we have to work with that. And then, of course, people do all sorts of crazy things. Now, what's a bad kind of plus? Well, there's actually a lot of them here. So I'll point out a couple. These kind of pluses that you see here are things which are what I would call a bad kind of a plus. Now, what makes them bad? Well, it's not that plus is bad, it's just that where they're at, it makes it harder to work with. So essentially, when I talk about a bad kind of plus, I mean something that's on the inside. And the reason I call it a bad kind of plus is it makes things more challenging to work with. Now, of course, a lot of students say, these aren't so bad. There's easy ways to fix that. So, for instance, some people might say, oh, look, here's this plus. Let's just do the following. Right, as 3x cubed over 2 plus 3x cubed over the square root of x squared plus 4. Now, what happens when we see that? Well, as an instructor, when we see that kind of action going on, our typical response is something along the lines of the following. We're just going to be crying. We're going to have tears flowing down our cheeks because of how sad we are, because this is just absolutely bad, terrible, terrible arithmetic. And so the thing is that not every plus sign is equally useful. Some plus signs are bad if you're done in the wrong way. So you have to learn to work with them. And one of the things we're going to be seeing, some of the themes that we're going to see a couple of times in the next few sessions, are how do we deal with this. In fact, this is not the first problem where we encountered having to deal with sort of a bad plus sign. If you think back here, e to the y plus 1 quantity squared, this is another example of a bad plus sign because it's inside the square function. And so you had to be like, okay, I have to deal with it. So that's another case where you had something that you had to deal with it. And if we go back to this other one, again, you had these plus and minus signs. Again, you have to deal with those. Those are on the inside. So be careful And a lot of what we're going to do is learn how to be careful. Don't make bad arithmetic. It's really going to mess you up. Make good arithmetic. Good arithmetic saves points. All right, well, that's it for our first session, and many more exciting sessions still to come. And I hope you have a good day. Bye.